Hello again, my physics students. This is Mrs. Buchanan, and this is flip video number 16. We're going to continue our discussion of momentum and conclude it as well with this flip video. First of all, let's go back and revisit our big idea. Momentum is conserved for all collisions as long as external forces do not interfere. We will be covering learning objectives 5 and 6 with this video. Learning objective number 5, describe how the conservation of momentum applies to collisions. The collision of objects clearly shows the conservation of momentum. Whenever objects collide in the absence of external forces, the net momentum of both objects before the collision equals the net momentum of both objects after the collision. Net momentum sub before collision equals net momentum sub after collision. We will be talking about two kinds of collisions. The first one is called elastic collisions. When a moving billiard ball collides head-on with a ball at rest, the first ball comes to rest and the second ball moves away with a velocity equal to the initial velocity of the first ball. We see that momentum is transferred from the first ball to the second ball. When objects collide without being permanently deformed and without generating heat, the collision is said to be an elastic collision. Colliding objects bounce perfectly in perfect elastic collisions. Perfectly elastic collisions are not common in the everyday world. We find in practice that some heat is generated during collisions. Drop a ball, and after it bounces from the floor, both the ball and the floor are a bit warmer. Even a dropped superball will not bounce to its initial height. At the microscopic level, however, perfectly elastic collisions are commonplace. For example, electrically charged particles bounce off one another without generating heat. They don't even touch in the classic sense of the word. So the sum of the momentum vectors is the same before and after each collision. So if we go back to our billiard ball, the moving billiard ball collides head-on with the ball at rest. The first ball comes to rest. The second ball moves away with a velocity equal to the initial velocity of that first ball. They do not continue indefinitely with that momentum. The external force acts upon them, and friction with the table and the air also intercedes the collision. Inelastic collisions. A collision in which the colliding objects becomes distorted and generate heat during the collision is an inelastic collision. Momentum conservation holds true even in inelastic collisions. Whenever colliding objects become tangled or coupled together, a totally inelastic collision occurs. So let's look at two freight train cars. Suppose the freight train cars are of equal mass, small m, and that one car moves at 4 meters per second toward the other car that is at rest. Can you predict the velocity of the coupled cars after impact? If we look at the conservation of momentum, net momentum sub before collision equals net momentum sub after collision. Or if we look at equation form, parentheses net mv parentheses sub before equals parentheses net mv parentheses sub after. So you would take m times 4 meters per second plus m times 0 meters per second equals 2m times v sub after. Since twice as much mass is moving after the collision, can you see that the velocity v sub after must be 1/2 of the 4 meters per second? Solving for the velocity after the collision, we find v sub after equals 2 meters per second in the same direction as the velocity before the collision, which is v sub before. The initial momentum is shared by both cars without loss or gain, and momentum is conserved. So most collisions usually involve some external force. If we looked at our billiard balls, we know they don't continue indefinitely with the momentum that's imparted to them. Same way with a pair of space vehicles. They dock in orbit, they have the same net momentum just before and just after contact. Since there is no air resistance in space, the combined momentum of the space vehicles docking after is then changed only by gravity. Next to learning objective number 6. Describe how the vector nature of momentum affects the law of conservation of momentum. Momentum is conserved even when interacting objects don't move along the same straight line. To analyze momentum in any direction, we use the vector techniques we've previously learned. The vector sum of the momenta is the same before and after a collision. We'll look at momentum conservation involving angles by briefly considering two examples. We have the momentum of car A, and it is directed due east. Car B is directed due north. If their momenta are equal in magnitude, after colliding their combined momentum will be in the northeast direction with a magnitude of the square root of 2 times the momentum either vehicle had before the collision, just as the diagonal of a square is the square root of 2 times the length of a side. We also have a falling firecracker that explodes into 2 pieces. The momenta of the fragments combined by vector rules to equal the original momentum of the falling firecracker. We'll go more in depth than that into class when we go over our flip video. So conservation of momentum and conservation of energy are two of the most powerful tools of mechanics, and so we will be moving into talking about energy upon conclusion of this chapter. Thank you.